Section 4.4 is dealing with the ideal gas law, and this is your last mastery quiz of the gases unit. When we're dealing with all of the gases law, what we're doing is we're assuming that every gas is an ideal gas. So an ideal gas does not actually exist. It's a hypothetical concept. And an ideal gas, the first point about it is it's going to follow all gas laws perfectly under every condition. And again, this is something that doesn't exist. An ideal gas will not condense, and an ideal gas is assuming that the particles have no volume and that they are not attracted to each other. Again, these are all conditions that do not exist. A real gas, however, doesn't follow the gas laws exactly. It is going to deviate, meaning not follow the gas laws, at low temperatures and at high pressures. A way you can think about that is at the very bottom of the ocean, it would not follow the gas laws, because at the bottom of the ocean, it's really low temperature and really high pressure. So a real gas will condense to a liquid, and sometimes it'll actually condense to a solid if it's cooled or if it's under pressure. The particles are attracted to each other, and the particles have volume. However, it will behave at an ideal gas at higher temperatures and lower pressures. So the first diagram here is showing what it would look like for a collision in an ideal gas. Remember, a collision has to happen in order for reactions to occur. So in an ideal gas, you can picture the gas molecules looking kind of like marbles. So they are going to move towards each other very fast. When they crash into each other, they are going to not change shape at all. And when they rebound away from each other, they're going to go very fast. They're not losing any speed, and they're not changing shape at all. In a real gas, you can see they're still coming together quite fast at each other, but you can kind of think of them like water balloons. So when the molecules of the real gas crash into each other, they're going to kind of go gadunk like a water balloon, and then when they move back away from each other, they're going to be moving slow. When we're dealing with any sort of gas in this unit, we're going to always be dealing with it as if it was an ideal gas, as we've been doing so far, because we need to be able to use an ideal gas to make our gas laws work well. The ideal gas law is how we are going to mathematically represent ideal gases. And what the ideal gas law is doing is it's looking at pressure, temperature, volume, and the amount of gas, or the mole of gas. And these are the four variables that we're able to measure, and the four variables that do define a gas system. If you look on the bottom here in the brownish box, you can see that the ideal gas law is PV equals nRT. Generally, people remember this by saying pervnert, because it kind of sounds like pervert. Although you don't need to know how the ideal gas law is created, it's important to understand it. So Boyle's law, we know from Boyle's law that volume is inversely proportional to pressure. This symbol right here is the proportionality symbol. What that means is that when volume goes up, pressure will go down. Charles' law says that volume is directly proportional to temperature, meaning when one goes up, the other one will also go up. Avogadro's theory is that the volume is directly proportional to moles, again, which means when one goes up, the other one will go up. From all of these comparisons, we can put them all together into a formula right here that volume is proportional to temperature multiplied by moles divided by pressure. In order to get rid of the proportionality symbol, what we have is we have a constant called R. R is the universal gas constant, and it's a constant that was created by putting STP conditions and SATP conditions into this formula. And R is a number that we are always going to use as a constant and memorize and use into our ideal gas law. So again, at the bottom, the ideal gas law is PV equals nRT pervnert. So R is the universal gas constant, and R is going to be dependent on whether you're using kPa or ATM. There's two different values for R. They're in the box up here at the top. You can see that the top value for R, 8.314, is liters times kPa per mole Kelvin. That is the value that you're going to use when you're using kPa. And the second value, 0.0821, liters per ATM mole kelvins, that's the value that you're going to use when you're using ATM. So what you're always going to do is you're going to look at the value, or look at the pressure unit that you're using, and then use the appropriate R value dependent on the pressure. R was found, you can see at the bottom, by subbing SATP and STP conditions into the pervnert gas law. So what we have here is we have the ultimate mole map. So You see up here on the left is concentration. That's how we got from moles per liter to moles in Chapter 5 for solutions. On the top right, we have mass. That's when we use our molar mass to get to moles. On the left here, we have the number of particles, and the number of particles is when we're using Avogadro's number. What we did in Mastery Quiz 3 is the bottom here. We used our molar volume to figure out the gas volume if the gas is at STP or SATP. And what we've just added today is if your gas is not at SATP or STP, you are going to have to use Pervnert. Okay, we're going to do 3 examples. What I would suggest you do always with the ideal gas law is write down your variables first. You're always going to have 5 variables. If you know 4 of the variables, then you can solve for the last one. So example 1 here is asking for mass of neon gas and how much should be introduced into a 0.88 tube to produce a pressure of 90 kPa at 30 degrees Celsius. So from that we have pressure, we have volume, we have temperature, which again we're changing into Kelvin all the time. We will always have R, and we're choosing 8.314 because it is the kPa value. And we do not have moles, and we do not have mass. So what we're going to need to do first is find moles, and then after that we can find mass. So what we're starting with is we're starting with PV equals nRT. Because moles is what we're looking for, we need to get moles on one side all by itself. In order to do that, we have to divide both sides by RT, and divide this side by RT, which means now we are going to have N equals PV over RT. What I've done here is I've subbed in all of my numbers to my formula, and the units for your R are making sure that unit analysis-wise we can cancel out all of the other units in the formula. And we can solve for N by doing 90 multiplied by 0.88 divided by 8.314 divided by 303 is going to get us an N value of 0.03149 moles. And we're not going to round yet for significant digits because we need to wait until we get our final answer, which needs to be in mass. In blue at the top, I've just written down the molar mass for neon gas, which is 20.18. So we now need to take the moles and figure out our grams using our molar mass. So on the left, you can see in blue what I'm doing is I'm taking the moles that I just calculated. I'm going to multiply that by the molar mass, which is 20.18, and I will get my final grams, which the grams are going to equal 0.63 grams. And I'm keeping 2 significant digits because I had 2 significant digits in the question. And again, we're not looking at temperature for significant digits. Okay, this question has given us our volume. It has given us our pressure, and it has given us our temperature. The temperature down here we're always converting into Kelvin, and our R in this case, because we're using ATM, is going to be 0.0821 liters per ATM mole Kelvin because we want to use our ATM. I'm going to start with my formula, equals PV equals nRT. I'm looking for N, which means I need to put N on one side all by itself. That means I'm dividing both sides by RT. And RT, which means the RT on the right cancels out, and I am left with N equals PV over RT, which I can sub my numbers into. So I'm going to do 20 multiplied by 2 divided by 0.0821 divided by 300 is going to get me an answer of 1.624 moles. And because the answer's asked for moles, that means I'm paying attention to my significant digits right now, which means I'm going to keep 1.62 moles. This question says predict the volume, which means my volume is my question mark. It gave me 0.78 grams of hydrogen, it gave me my temperature, and it gave me my pressure. When I write down my variables, I'm going to put down my formula, which is PV equals nRT. What I have so far is I have my pressure, it gave me my pressure, volume is my question mark, I have R all the time, and it gave me temperature, which means I have 2 unknowns right now. I have volume and I have moles. But I do have mass, and I first have to use my mass to figure out my moles. I'm going to do that by using my molar mass. So I'm going to take 0.78 grams, and because hydrogen is H2, that means its molar mass is going to be, for 1 mole, I'm going to have 2.02 grams. And my moles would be 0.386 moles. In my calculator, I'm not going to round this number because I want to make sure that I am not influencing my answer. Now that I've calculated my moles, I can rearrange my formula for volume which means I need to divide both sides by P because I need to get V on one side all by itself, cross out the P's, and then what I end up with is V equals nRT over P. So I have V equals nRT over P. I need to sub in all of my variables now. So I'm going to do 0.386 multiplied by 8.314 multiplied by 295 divided by 125 is going to give me a final volume of 7.57. And remember, I didn't round my moles, so I put in my entire mole value. So I have 7.57, but significant digit-wise, I am going to keep 2 significant digits, which means I am going to have 7.6 liters as my final volume. These are the demands associated with Mastery Quiz 4, and if you want some extra practice, here are some more ideal gas laws extra practice questions. Good luck!